Okay, the last section of chapter 8 is applications with determinants. We'll do most of the section today, and then we will do one last topic next class. Okay, so the first application of determinants that we're going to learn is called Cramer's rule. So to solve a system, depending on the number of variables, if it has x and y, it would be this. If it was x, y, z, it would keep going. If it was w, x, y, z, it would continue with the same pattern. If I want to find the x coordinate, I do dx over d, where dx is the determinant of the coefficient matrix with the x column replaced with the constants, and then d is the determinant of the coefficient matrix. So for example 1, I'm going to solve the system using Cramer's rule. And I'm going to keep in mind what my answer is going to look like. My answer is going to look like dx over d, comma, dy over d, because I want to get an x and a y because there's two variables. Okay, so first I'm going to calculate d. Okay, now d is the determinant of the coefficient matrix. The coefficient matrix is the stuff over here because it has the x's and the y's. It's the coefficients. So I'm finding the determinant of this thing, which is a 2 by 2, which makes it pretty easy. This would be negative 20 minus negative 6. So I get negative 14. Okay, now I'm going to go ahead and find dx. Okay, now remember, dx is the determinant of the coefficient matrix with the x column replaced with constants. Okay, so I want to copy the coefficient matrix again, but instead of the x column, I'm going to put these numbers over here. So instead of the x column, I'm going to put the 10 and the 11 that were the constants, but I'll keep the rest of the matrix the same, which means it still has a negative 2 and a negative 5. Okay, and then I'll go ahead and calculate the determinant of this, which is very quick because it's a 2 by 2. Okay, and then the last thing I want to calculate is dy. Okay, for dy, I'm going to use the coefficient matrix again, but this time I'm going to replace the y column with the constants. So it'll still be 4 and 3, but instead of using the negative 2 and negative 5 for the y's, I'm going to replace that with the 10 and the 11. Okay, so 44 minus 30 is 14. Okay, so I found all the things I need to calculate the answer. Now, if I want to go back and actually calculate the answer, let's see, dx is negative 28, d is negative 14, comma, dy was 14 over negative 14. So the answer to the system would be 2, comma, negative 1. So it's just another method for solving the system rather than elimination, substitution, or reduced row echelon form. Okay, so now we're going to try to use Cramer's rule again, but this time we're going to have 3 variables instead of 2. So I'm going to need the d, the dx, the dy, and the dz. Okay, let me start with the d. Two, 0, 1. Okay, so this is a 3 by 3 matrix. You can use the cofactor method or you can use the diagonal method. I leave it up to you. For this example, I'm going to use the cofactor method. In a later example, I'll use the diagonal method so you can kind of see a reminder of what both of them are. Okay, if I use the cofactor method, I'm going to select a row or column that looks easier to me. I'm going to select the second row to go along, and that's only because it has a 0, so it's one less thing for me to calculate. Okay, before I start, let me consider the signs of the cofactors. Okay, so if I start up here, this is positive. If I go down, this must be negative, and if I follow the pattern, it alternates negative. Okay, so let me get this set up. This is going to be negative 2 times the minor plus 0, and I'm not even going to leave a space for the minor because it doesn't matter, it's getting multiplied by 0. Okay, so let me calculate the minor. At the 2, if I ignore the row in the column, then I'm left with 8 minus 12. Okay, I ignored the 0 term because 0 times anything is 0. So let me go to the 1. ignore its row and its column. So I'm left with, looks like 4 minus 6. So that's negative 2 times negative 4 minus 1 times negative 2. 8 plus 2 is 10 for D. Okay, let me try to do dx next. Okay, for dx, it's going to be the same matrix except for the x column. So I'm going to skip the first column, but I'll copy the other columns. Negative 3, 1, 4. And then the x column will get replaced with the coefficient matrix. 1, 0, 2. Okay, I'm going to find the determinant of this. Remember, you can use the diagonal method or the cofactor method. I'm only using the cofactor method to remind you of it. Okay, pick a row or column. What am I going to do? I'm going to go along row 2 because it has 2 zeros, which means way less work. Before I write it out, I'm going to consider the signs. If I start top left, that's a positive, which makes this a negative. So this is a negative, positive, negative. Not that it matters. So negative 0 times something is going to be 0, plus 0 times something is 0, minus 1 times the minor. So I only have to calculate one minor. So if I look at the 1, cross off its row and column, and then I'm left with 1 times negative 4. Negative 4 minus 4. So negative 1 times negative 8, which is 8. I'm going to go to dy next. Okay, and I'm going to keep the matrix exactly the same as the coefficients except the y column. Okay, and now the y column is going to be replaced with the constants, they're the solutions. I'll just keep using row 2. If I saw an easier row, I would switch, but I already know the signs. Okay, so it's going to be negative 2 times the minor plus the 0, which I don't care about the minor because it's going to go away, minus 1 times the minor. Okay, so for 2, ignore the row, ignore the column. And I'm left with 1 times 4. 4 minus negative 6, so 4 plus 6. Okay, and then the 0 I didn't care about because when I multiply by 0, it goes away. But if I go to the 1, ignore the row, ignore the column, and I'm left with negative 2 minus 3. Okay, let me calculate this real quick. Negative 2 times 10 minus 1 times negative 5. Negative 15. Okay, now I have to do dz. So dz, same as the coefficient matrix, except the z column gets changed now. So for the z column, I'm going to change it to 1, 0, 2. Oh, that turned out nice. Okay, I'm going to go along second row, and I can see that there's an extra 0 there, so I'm definitely going across that row. I already know the signs are negative, positive, negative. So negative 2 times the minor, plus 0 plus 0. No, plus 0 minus 0. It doesn't matter because they're all zeros, so it doesn't matter. Okay, so minor, cross off the 2, cross off the 2. What am I left with? 2 times 2, 4 minus negative 4, so 4 plus 4. Negative 2 times 8 is negative 16. Okay, that was a lot of work. Now I'm going to actually get to my answer. Okay, so for my x coordinate, it will be dx over d. For the y coordinate, it will be dy over d. And for the z coordinate, it will be dz over d. And I am going to simplify these because I'm not leaving it like that. Okay, so the answer to the system should be 4/5, negative 3/2, negative 8/5. This is the same answer as if I had used row echelon form or elimination or substitution or whichever method I prefer. Okay, now the next application involves the area of a triangle. So if they give you the 3 vertices of a triangle in the coordinate plane, you can use matrices to calculate the area. According to this formula, it says A equals plus or minus 1/2, and then they want you to set the matrix up like that. They don't actually mean plus or minus, and I don't like the notation, but that's what your book uses. They actually just mean that the area must be positive. So they want you to take the absolute value of the answer so that you end up with a positive area. But obviously, if you put absolute value, it's going to look like another determinant, and that's confusing. So what they really want to say is if your area is not positive, make it positive. Okay, so let's just see what the setup looks like. This is not that bad, it's just setting it up one time. Okay, so according to the area, it says plus or minus 1/2. I'm going to leave it 1/2. And then later on, I will go back and fix it based on if it's positive or negative, because they really want me to do absolute value. So it says x1, y1, 1. So for my first ordered pair, I have 1, 0. For the next ordered pair, I have 2, 2. Third ordered pair, I have 4, 3. And then I'm just going to keep that third column always ones. Okay, so I just need to find the determinant of that little matrix. Okay, I will use the diagonal method this time so that the people who like the diagonal method could see their method reiterated. Okay, so if you recall with the diagonal method, I rewrite the matrix 0, 2, 3, 1, 1, 1, and then I add the first and second column repeated. 1, 2, 4, 0, 2, 3. I'm going to start on the top left and go diagonally. See, I'm not good at the diagonal method because I can't write straight. Okay, 1 times 2 times 1 is 2, plus, let me go down the next diagonal. 0 times 1 times 4 is 0, plus 1 times 2 times 3 is 6. Okay, and then I have to subtract the opposite diagonals. I need a bracket here, don't I? Okay, now I'm going to go in the opposite direction. I'm going to start on the bottom left. Try to draw your matrix straighter than me. 4 times 2 times 1 is 8. Okay, let's try the next one. 3 times 1 is 3. 1 times 2 times 0 is 0. Okay, so I'm going to have 1/2 of 8 minus 11, which is 1/2 of -3, which looks like it's going to be -3/2, but because it's area, I make it positive. And I'll just make a note. I made it positive only because it's area and it has to be positive. Okay, so really take the absolute value when you're done, but don't put those bars because then it looks like determinant again. Okay, so that's the area of a triangle. Okay, one last application for today, and it's very similar to the triangle one, except for it has to do with lines. So what actually happens is that if you set up the matrix very similarly to what you did for the triangle, if you calculate this and it equals to 0, the points are actually collinear, which kind of makes sense with the triangle, because if you had the area of the triangle ended up being 0, then it must be true that you actually didn't make a triangle. Those points line up, and that's why your triangle is completely flat and has no height and must be collinear. Okay, then related to that, if you want to find the equation of the line, you keep variables x, y in one of the rows, use 2 ordered pair, set it equal to 0 because that will make sure it's a line, and you can find the equation of the line that way. So I'm going to show you doing each thing, how that would look. So if, for example, 3 had asked, are these points collinear? So I'm going to set up that matrix just like we did for the triangle. So the first point is 2, 4, 3, -1, 6, -4. The third column is 1s. There is a proof in your book about this. I haven't read it though, so I actually don't even know why this works. It's just kind of cool. Okay, so if this equals to 0, it would mean they were collinear. If it doesn't equal to 0, it would mean they were not collinear. Okay, let's see. I'll do the diagonal method for those who like it. I'm going to try to draw straighter this time. -4, 1, 1, 1. Repeat column 1, repeat column 2. Okay, I did a better job this time. Okay, I'm going to start on the top left. This one, this one, this one. Okay, so -2 plus 24. That was supposed to be a -4, huh? Minus 12. Okay, minus. Okay, now I'm going to do the diagonals in the opposite direction. This one, this one, this one. I did draw it better this time. Okay, so that's -6 minus 8 plus 12. So this equals to 22 minus 12. 10 minus -2. 10 plus 2 is 12. So not collinear. If they ask why, it's because the determinant is not equal to 0. The determinant was 12 instead of 0. If it had been 0, then I would have known they were collinear. But because it's 12, that means the area of the triangle formed by those points is actually 6. Okay, the last thing is I'm going to write the equation of the line given these points. I could also use slope-intercept form or point-slope form, but in the directions it's going to say use matrices. Okay, so I'm going to set this up. Okay, because I want my equation to have x and y in it, I am actually going to put x and y in my first row. Although they could be any row, it would be fine. My next point is 2, 4. My next point is -1, 3. And the third column is 1s. Okay, I'm going to set this equal to 0 and calculate the determinant. Okay, I'm going to use the diagonal method. But if you use the cofactor method when you're doing the equation of line, it turns out really nicely. Maybe I'll show both ways. Okay, so let me set this up for my diagonal. Okay, so I rewrote the matrix and I wrote the first and second column repeated. Start on the top left, so this one, this one, this one. So that's 4x minus y plus 6. Okay, now if I start on the bottom left and do those diagonals, this one, this one, this one. -4 plus 3x plus 2y, and that should equal to 0 for this to be a line. Okay, and then you just need to convert it to some kind of simplified standard form. I'm not that particular about which kind of form. Plus 4. Okay, if you left it like this would be fine. First, in some cases, this is considered standard form. If you move the 10 over, that's fine. If you make this slope-intercept, that's fine, as long as it's in some kind of simplified standard form. Okay, if you're done with it, if you're happy, you can stop the video. I'm going to show that using the cofactor method, this actually works out really cleanly. So if I wanted to use the cofactor method on this, and if I went along row 1, except I don't want to write on it, mess it up, whatever. Okay, I go along row 1. Okay, if I want to find the determinant, it would be x times something minus y times something plus 1 times something equals 0. Okay, so if I ignore x and x, I have 4 minus 3.